Hello, everyone. It's a great honor to share my research about end-to-end robustness for sensor reasoning pipeline in adversarial environments here with you. My name is Bo Li, and I'm system professor from UIUC. As we all know that machine learning nowadays has been ubiquitous in the world. It has been applied to different domains to help make our life better. For instance, autonomous driving, intelligent medical treatment, and smart city have been built up to improve the quality of our life. And AlphaGo has shown that the AI has certain power which can perform better than human on certain tasks. However, even such very powerful machine learning techniques have also brought a lot of security and privacy concerns for us. For instance, in 2016, the White House associate Twitter account was hacked via phishing emails, which spread the rumor that the White House has been attacked. And it triggers the autonomous trading bot to dump a large amount of stocks within seconds and swipe about $136 billion within seconds. And that's something happened in real world. And also in Australia airport, the biometric recognition system has been deployed for safety screening, which has raised a lot of privacy concerns. So with these concerns, we can also look at some real-world examples and think about what even if we are facing such vulnerabilities of the machine learning models, what we can do to improve the robustness and towards the trustworthy machine learning or AI. So here is our previous result showing that given the real-world stop signs, which may contain some graffitis or certain patterns on the sign itself, we actually show it's easy for a human to generate certain adversarial so-called stickers that can be stick onto the stop sign itself in real world. And you can see here each column is a different types of adversarial perturbation in real world, and each row shows different angles and distances. And this shows that with certain adversarial behaviors, it's possible that all the stop signs in these slides are misrecognized as speed limit sign 45, which can raise severe consequence if a car will not stop when they see such adversarial physical stop sign. And here is a quick example that dynamic experiment that when there is a car driving by, on the left-hand side is a perturbed stop sign, and on the right-hand side is a control experiment, which is a vanilla stop sign. And if we look at the captions, we can see with different speed and the distances of the car, the left-hand one is always misrecognized as a stop sign. So this actually raises us a lot of thinking about, okay, we know in real world, we can exactly see that the machine learning systems, either autonomous driving or medical treatment, which are mission critical here, can be manipulated in certain way by adversaries, so that cause severe consequence. So in this talk, I will mainly talk from three perspectives to look at how and what strategies we can use to improve the robustness of machine learning models, so that we can certify the end-to-end robustness, or we can verify the sensitivity or the stability of the machine learning models, such that we can end up with a more trustworthy machine learning or AI systems. And the first, we'll talk about the certifiable robust sensor reasoning pipeline, and then we'll talk about how to leverage game theoretical analysis to analyze the robustness or vulnerability of machine learning models, and then I will talk about the other intrinsic information that can be leveraged in either the data or machine learning model itself, such that we can improve the robustness of machine learning models. So first, let's look at this end-to-end robust sensor reasoning pipeline and see what guarantee we can obtain here. And here is a higher level overview of this framework. So we know that as machine learning has been applied to many mission critical scenarios, certifying the machine learning model robustness has become increasingly important. And many previous work, however, only focus on the robustness of independent machine learning or even just ensemble models, and only certifying a small magnitude of the perturbation from the adversarial perspective. So here in this sensor reasoning pipeline, the goal is to promote the generic sensor reasoning pipeline here, which can contain both sensing components, which you can see on the left-hand side is a bunch of you can view it as a bunch of neural network models, or it can be other machine learning models, logistic regression, decision tree, whatever machine learning model or statistical machine learning model it is. And then we compose it with a reasoning component, which can be realized as Markov logic networks or Bayesian networks, which is graphical models can incorporate domain knowledge. And then we can enrich the domain knowledge with these graphical models. And the question we want to ask here is, can the domain knowledge help improve the learning robustness, and how much we can formally certify this end-to-end robustness for this sensor reasoning pipeline? So this is a question we want to ask. And here we can see there are additional challenges and opportunities within this pipeline. So concretely on the sensing component phase, we actually have the neural net. For example, we take the example of neural networks, and who can output their prediction as a set of Boolean variables. And this set of Boolean variable can be viewed as a prediction for certain classes. And those Boolean variable can be sent to the reasoning component, which will use this set of Boolean random variable in the statistical reasoning models, and then to produce the final output, which is also a set of Boolean variables. And this pipeline can actually be applied to a wide application, such as reinforcement learning and information extraction, which I will show some experimental results later. But let's focus on the theoretical analysis first. So we can see that given such a pipeline, our goal is to certify that during the inference, given a perturbation at the input, which is the eta here, like take the image as an example, we have certain magnitude of perturbation added to the image, just as adversary examples. And then after passing this reasoning pipeline, we have some uncertainty at the output of the reasoning component, which is a CS here. And this uncertainty will again be passed to the reasoning component, and then we will eventually get the final uncertainty, which is a CE here. Our goal here is to bound the CE given the knowledge of eta here, so that we can bound the end-to-end robustness. And we will give the formal definition in the next slides. So here I mainly want to emphasize that there are both challenges and opportunities for this pipeline. For example, in terms of the challenge, we can see that different from the neural networks whose inference can be executed in polynomial time, but the many reasoning models such as Markov logic networks, which we know can be Sharpe complete for during the inference. So this raise the hardness for the computation. However, this also gives us the opportunity because as many reasoning models define a probabilistic distribution in the exponential family, so we have more function structures than in neural networks that we can leverage and potentially make coming up with robust guarantees, which essentially make the solution for a min-max optimization problem on top of the graphical model reasonable. So here, in this sensing reasoning component pipeline, we'll mainly talk about two questions. One is checking the provable robustness in the reasoning component feasible when the inference of the reasoning component is Sharpe complete, right? And we will show it is possible and we can compute it efficiently. And second, we'll show when we can efficiently compute it, how we can guarantee the end-to-end robustness given some oracle towards the statistical reasoning, meaning we know what's the knowledge we want to incorporate in the reasoning component. Okay, so next, let's look at a concrete example of how we can incorporate certain knowledge into the this sensing reasoning pipeline. So we can see more concretely here we have a set of sensing sensors, and we call SI. And then we have a reasoning component, which is R. And for each sensors, they will output a probability for certain classes, which we call the PIX, given the input data X. And the output of a reasoning component is the new Boolean variable based on the output of the sensing model, which is the R over the PX, and take the expectation over it. So we can see that one example of such knowledge is for ImageNet classification. So we know there is a hierarchical knowledge for ImageNet dataset, and here the sensing model corresponding to the classifier for each specific class in the ImageNet. For example, here it's a sensing dog or the sensing animal here, and the reasoning component here output a Boolean variable for each specific class, and the reasoning component then endorses the domain knowledge, such as if an image is classified as a dog, then it must be classified as an animal, such hierarchy knowledge. So we can see here in each sensing, they output the dog or cat or animal, and then for this output of the sensing models, there is a factor graph which can incorporate the factor among these sensors, so that we can learn the weights later for each factor within the graph, and emphasize different types of knowledge. And next, let's have the formal definition of our end-to-end robustness for this sensing reasoning pipeline. So basically, we can see if given the CI/CE, which is the input, the magnitude of perturbation bounded for the input data and the output of this end-to-end pipeline, and we hope we can bound the output of the reasoning component given the input and the perturbation of the input. So we know no matter as long as the input of the perturbation is within certain range, for example, CI here, and we know the end-to-end output for this pipeline will be bounded by CE. So that's our goal. And here are some specific variables we will use later on in our analysis. So basically, we know there are, within the reasoning component, there are some interface variables which connect with the sensing models, and there are some interior variables within the reasoning component or the graphical model component, and we have different factors for these two types of variables as well. And we can see on the higher level, the output of the MLN reasoning component is that it's a probability of Z1 divided by Z2. So here Z1 defines the possible word that makes the knowledge true, and the Z2 defines all the possible words that can happen in this graphical model assignment. So basically, from this high level intuition, you can see the hardness of calculating how many assignments are possible here within this graphical model becomes the main bottleneck for our computation. So here we will first look at the hardness of this problem of the for certifying the end-to-end robustness for this sensing reasoning pipeline, and we can see that given this Markov logical model as an example, we can show the above the graphical model itself can define a joint probability distribution among all the variables, and for each possible word, they design a set of assignment for the possible word. And here we have the definition for counting problem, which exactly counts the assignment for a set of first order logic rules. And we can see when we write it in this way, it looks very close with the formulation as the robustness that we want to certify here, which is we just rewrite the robustness as the second definition. And here we can see we can reduce the robustness of sensing reasoning model to the counting problem, which shows that the end-to-end robustness certification for the sensing reasoning pipeline is Sharpie complete. However, a good news is that it's still possible to give the provable robustness for the end-to-end reasoning component here, even though the inference time, the factor graph inference is Sharpie complete, but given certain knowledge, for example, there are multiple ways to accomplish this. For example, when the factor graph is of a small tree-wise, or one can apply exact inference algorithm for it, or one can also construct the Markov logic net program such that exact statistical inference is possible. Or there also exists a range of approximation inference algorithm for ML and inference. So here we can show that as long as we have access to an exact oracle for the statistical inference, then provide a novel algorithm for the upper and lower bound of this sensor reasoning pipeline is possible. So here is how we can do it with this lemma. So basically we can see with the magnitude of perturbation as C, we can exactly solve the max problem here given the min-max structure. So basically we know even in the traditional neural networks, when we want to certify the robustness of it, we are trying to essentially solve a min-max problem. And because of the non-convexity and non-monotonicity of the neural networks, solving exact min-max problem for it is hard. But here, because we have some knowledge about the possible world due to the domain knowledge we can get, it is possible for us to solve the min-max problem here. So we can see here, remember that the D1 defines the possible words that give you the ground truth assignment aligned with the knowledge, and Z2 defines all the set of possible words. And we can see the conclusion is that when we have a ratio lambda larger than 0 or the smaller than -1, we can exactly get the solution for this min-max problem. And if the lambda is within -1 to 1, we have to sample with MCMC and then bound it to analyze the magnitude here, the epsilon here. So that is to say, with exact knowledge about what can be true in this sensing reasoning pipeline, it is possible to certify the end-to-end robustness. So on the high level, I want to give some intuition about why it is possible. So the fundamental reason lies in the structure of the reasoning component. We can see here with a range of properties. For example, all variables are factors are only output non-negative values. Unlike in neural network, it could range from negative to positive. This makes it possible. And also the distribution is in the exponential family with a limited weight sharing, and the reasoning component also enjoys some monotonicity properties. For example, with this like 1 lambda larger than 0, it monotonically increases. So in this way, because of the non-negative and the monotonicity properties, the min-max optimization problem becomes solvable here in the MLN program compared with traditional neural networks. And moreover, these properties hold for general morphologic networks, which is good, and make us believe that this sensing reasoning pipeline provides a unique opportunity for us to further improve the robustness of ML applications by integrating different domain knowledge, especially given that the robustness of a single machine learning model or ensemble can be harder to certify in real world. So here, I think this sensing reasoning end-to-end pipeline actually give more promising way for us to certify the end-to-end robustness in real world for machine learning models by incorporating human knowledge to it. And here I want to, after the theoretical analysis, we show that even though it is hard, by accessing some knowledge, for example, the domain knowledge and giving the constraints for approximating the MLN inference time, we can get the end-to-end robustness for different sensing reasoning pipelines. Here, empirically, will show how tight it is. Of course, in theoretically, we can show it is tight for MLN program at least, and it is also possible for some structures for Bayesian networks. And empirically, we want to show whether it can improve in practice for state-of-art applications. For example, here there are two applications. One is state-of-art OCR digit recognition model, and second is NLP stock data sets for information extraction. And here we can see different tables shows the with and without knowledge, and we calculate the end-to-end accuracy empirically or the certified accuracy. And here we can see if shown shows the magnitude of the input perturbation. And we see that with a larger magnitude of such perturbation, with knowledge like this sensor reasoning pipeline can certify much higher both vanilla benign accuracy and the certified robustness accuracy than the machine learning model without any knowledge. So this is showing that with human knowledge, it is possible to not only improve the benign accuracy of the sensor reasoning machine learning model pipeline, but also the certified robustness accuracy. And similar for other scenarios as well. And besides showing the benign accuracy and the certified robustness accuracy improvement, we also want to show how tight the robustness certification could be when we incorporate some domain knowledge. For example, again, this is 2 examples on OCR and NLP applications, and this the magnitude of the bar or the height of the bar shows the certified margin, which is the lower bound of the correct class minus the upper bound of the wrong class. So basically, the higher means the more confident it is. And here we see, for example, from the OCR experiment, on the left-hand side, the green background shows the correct, and on the pink one shows incorrect, and the blue one shows with knowledge, and the red one shows without knowledge, which is only a single neural network. And we see that with knowledge, when the perturbation magnitude is small, almost all the blue bars are in the green range, meaning that the blue bar are very confident to correct the prediction to the right range with high confidence. But more interesting, we find that sometimes when the magnitude of perturbation is very large, it is possible that we can see some blue bars are in the pink range, meaning that with knowledge, I'm actually more confident to drag the prediction to be the wrong class, meaning even I'm wrong, but I'm quite confident because I have the knowledge. So this is very interesting, but unfortunately, we hope will not happen in practice. So one solution to this is we still need to improve the robustness of the knowledge itself. So here, for example, we are using the knowledge as the hierarchy, right? Like if you are a dog, you should be the animal. However, this knowledge is actually not that robust because the assignment for certain first order logic rules are not unique. So it means you can have different assignment and some assignment could be wrong. So this way, the knowledge itself is not robust. So next, interesting direction, I think, for this end-to-end sensor reasoning pipeline is that we need to find the robust knowledge in terms of the uniqueness of the assignment for certain first-order logic rules. And then that will, for sure, confidently correct the prediction of any perturbed input for machine learning models. So this is the interesting future direction. And the quick takeaway from this robust end-to-end sensor reasoning pipeline work is that we show that it is possible to certify the end-to-end robustness of a sensor reasoning machine learning pipeline, although the robustness of the reasoning component is sharply complete in general, and giving oracle to the statistical inference, meaning we know the oracle how to calculate the possible word given the domain knowledge, and it is possible for us to efficiently calculate the certified robustness bound. And in practice, we know knowledge can indeed improve the certified end-to-end robustness for machine learning model pipeline, which can actually help to certify a larger magnitude of perturbation compared with current certified robustness for single neural networks. However, the important next step for us is to understand and efficiently collect robust knowledge to improve the certified end-to-end robustness. So after this end-to-end sensor reasoning pipeline is very interesting, and then but here we can we show knowledge is useful, like human knowledge is useful, but how to proactively obtain human knowledge and try to have an interactive behavior with adversaries to improve the robustness or certify the robustness is very important. So next we want to discuss a potential way that can leverage the game theoretical analysis to improve the robustness of machine learning models. And here is a very simple example for spam filtering. So we know here, for example, there is a spam filter, and this shows cheap mortgage, and this filter email is classified as spam based on, say, back and forth features. And then we can show, because of this cheap and mortgage are the words that have very high values, which we call spam features, that the email here can be correctly classified as a spam. However, if we have an attacker who wants to evade such detection, he can cleverly add some good words like the joy and organ, which will not affect the original meaning of this email, but unfortunately it will lower down the score of the whole email because the good words have low weights here, and then it will be misrecognized as a ham, although it's still a spam email. So we call this a spammer version 1. And with this, what the attacker can do, right? So what the attacker is, what the defender can do. So essentially what they can do is, again, put this like a spam instance back to the original training data to train it again, just like the adversarial training approach that we widely use now. And then this time it can give you another set of weights to the features, and again it can be correctly classified as a spam, and we call it as a spam filter version 2. And we can see this process can go on and on forever, like we can have spammer version 3 and spammer filter version 4, etc., and which will form as a repeated game. But we can see this is very hard to solve, and our goal is to formulate this repeated game in a way so that we can leverage the game theoretical analysis to solve this game and improve the robustness of machine learning models. And here we'll introduce the Stackelberg game to model this process. So in a Stackelberg game, there are usually two parties. One is a leader, one is a follower. So the leader will commit to some strategy. For example, here, the leader is a learner who will commit a strategy, which is SD. Basically, take the example of the spam before. The committed strategy is the classifier GX here, which can classify the benign spam here, and the adversary will be the follower in this case, who will best respond based on the committed strategy. So here we can see, assume the attacker has an oracle which can manipulate the original instance. So the attacker, what can do is that he can manipulate the XA, which is say the spam or malware here, so that it can just slightly pass the decision boundary and lead the detection, evades the detection, such that the spam can still have its functionality. So more concretely, we can see here the learner commits to some strategy as D, and the adversary will solve some oracle and generate X prime for each adversary instance. So that in this case, the learner's goal is to minimize the loss considering the potential adversary strategies. And here we can see there are two goals for the defender. One is the adversary cannot find any additional manipulations, which is ideal but very hard. And another is that the adversary can encounter too high manipulation cost so that it will stop to manipulate the system again. And here we can see the most important part is the oracle here. And there are two ways to model the oracle for the attackers. One is mathematical modeling, and one is use human subject experiment to show what the in real world attacker can do. And in this talk, we'll mainly focus on the mathematical modeling for the adversary strategies. And still take the example of the spam we had before. Given an attacker, there are several things the attacker can do. And first, the attacker have a cost in game theoretical analysis. And the cost means that if you manipulate the original malicious instance XA into certain instance X prime, what's the cost for it? Like the example in this spam, meaning the cost means that how many words you change, basically. And by minimizing this cost, the attacker's goal is that such that the manipulated instance will be able to evade the detection, meaning that the detection F delta will smaller than some predefined threshold. So here we can see the cost function is the word manipulated, and this is the F here shows the feature selection, which means what's the most important or robust features that you should select as a defender to defend against the such adversarial manipulation. And the third is the threshold here, because we know if we have a static threshold, the attacker can, if the attacker has the knowledge, it can potentially evade it. However, with dynamic operational decision, with prior knowledge of adversary behaviors, it is possible for the defender to generate some thresholds dynamically based on the ability of attackers, so that it is hard for the attacker to guess it. So we will go to each component briefly and see what can be the best strategy for each component selection. So first, let's look at the cost function. Traditionally, for the cost function, usually people use the distance-based cost function. For example, if you have a XA and XA prime, and then you calculate for each individual features, whether it is manipulated or not, multiplied by the weights, and you sum the manipulation up. However, let's see what's the drawback for these types of distance-based cost function. Again, take the example of the spam. We can see on the left-hand side, it's a spam, and on the right-hand side, it's a ham, and after manipulation. So we can see if we calculate, there are this many words manipulated. So if we simply count the number of words as a cost, the cost is 5 here. But if we can look at the difference, we can see some of the words here are synonym and some of them are letter substitution. So these types of, we call this substitution, can actually cannot hurt the adversary utility, because when we see a product, we also know it is a merchandise or weight, actually doesn't hurt us to recognize this as a weight, right? So this way, if we still use the distance-based cost function, we will underestimate the attacker behavior or attacker ability. So here, actually, in reality, there is only one word that we can count as a manipulation, and our others we can count as a substitution. So in fact, we should only use cost as 1 instead of 5 here. That is to say, in practice, in this game theoretical analysis, we propose to use this equivalent-based cost function, meaning that we want to first predefine some class here, feature class. Then for each manipulation, we'll check if the instances are within the same feature class, we'll view it as a substitution, and we will not increase the cost. Otherwise, we increase the cost. This way, you can better estimate the attacker behavior or ability, and the feature class is very important to define here. So I'll give a simple example of the feature class is a color. So for example, here we can see on the left hand side is a ground truth, which is a girl. On the right hand side are all the types of adversarial manipulations by manipulating the word. We can see the distance here could be very large because the colors are changed, but content wise, we can all clearly see it's a girl from the human perception, although it can be misrecognized by machine learning model as different other things. So that means we should count such semantic information as our cost function instead of the pure vanilla LP distance function. So this is important. And next, we will look at the feature selection component. And we can see on this simple figure, the x-axis shows the different number of features that is used to train the machine learning model, and the y-axis shows the error rate. And along the line, we can see with the lowest point corresponding to the optimal number of features that we should select to train a machine learning model. And this is the first class in machine learning model, which learned about the feature reduction, right? Or dimension reduction help to avoid the overfitting problem. However, we can see the purple line here is without considering any attackers, and the upper 3 lines here shows attackers with different cost budget. We can see when we consider attackers, optimal points shift to the right-hand side, meaning that even feature reduction can help avoid the potential overfitting problem. Such feature reduction can actually open a wide door for attackers to attack the machine learning models. Therefore, we should be very careful about dimension reduction, and actually using slightly more features will improve the model robustness in adversarial environment. And we show this phenomenon actually is true for different types of machine learning models and different types of cost functions. And therefore, later on we'll show how we want to make the trade-off between the feature reduction and the robustness. This is a very important trade-off that we should consider when we design the robust machine learning model algorithms. And the last one is a dynamic operational decision, which is very interesting and important in terms of developing a detection mechanism. For example, here as an attacker who want to minimize the cost function such that the cost function is smaller than some cost is smaller than some predefined budget, and the instance will be smaller than some predefined threshold. And here we can see as a defender, if they want to optimizing this problem, it is very expensive because with the dimension of the F here can be up to the dimension of the number of features, which it can be 1,000 by 1,000. So here we introduce like a general trick, which is leveraging a function Q of X to define a basis function. So the basis function is a set of Boolean functions, and such that we can learn this learn this Q of X based on a set of Boolean functions. So we can have we can learn only say 40 or 20 Boolean functions and optimize the weights for them, such that we can optimize a set of weights for dynamic optional decision for a classification problem. However, we show that the good thing is when the defender do this dynamic operational classification or detection, this attacking problem becomes NP complete for the attackers, which is great news for the defender. And here we still want to, as a defender, we still want to approximate some adversarial strategies such that we can improve the robustness of our models. So there are a bunch of approximation algorithms we can leverage to optimize the weights for each basis function. So gathering all the information we had before together will show how we actually can developing this robust machine learning model given the interaction with attackers. So in the traditional machine learning model, we can see we just want to minimize the loss function given the training data xi, such that the weights combined with instance training set instance xi, the loss function will be minimized. And in addition, when we consider attacker behaviors, we know within all the training data set, we want to select the ones which gives the positive classification, because this could be the target for attackers, right? And we want to manipulate this corresponding instance such that the cost will be smaller than some predefined cost budget, and the manipulated instance will evade the original classifier. So this is the adversarial strategy, right? So we consider this adversarial strategy during this optimization. And now the optimization becomes this way. So for the benign instance, we will minimize the loss function as before. For the adversarial instance, we will consider the adversarial behaviors and then use the manipulated instance back to the optimization objective function for the defender. And we will use this L1 norm to trade off the between the to make the trade-off between the robustness and the feature reduction we discussed before. And we can see here we can have the different benign, adversary, and trade-off for each component. However, solving this optimization problem is still hard because lots of nonlinear components here. So actually, we can linearize this optimization problem by these types of program, and it's fine. We don't need to look into detail about it, but the goal is to show it is possible to optimize or convert the original constraint optimization into this mixed integer linear program and solve it such that we can efficiently get the results based on the certain solvers. However, there are still some reasons for challenge. For example, there could be large amount of malicious instance that we need to optimize them each time, and there could be intractable amount of constraints for each instance, right? And the way to approximate it is that we can clustering all the malicious instance such that the hypothesis is adversary have some certain common goals, and they want to optimize the instance for certain classes. So we only need to focus on the representative instance within the adversarial clusters. And also for the constraint generation, we can use the best response and the hot start with adding the best response of constraints every time into the linear program solver to solve the problem. And essentially we can see by forming the interaction between the attacker and defender as the Stackelberg game and solve it, it is possible to improve the robustness and beat the state of art or the machine learning models. And this shows that it is possible to leveraging the interaction of game theoretical analysis between attackers and defenders to improve the robustness of machine learning models. However, there are additional information we want to understand because we can see in the game theoretical analysis there are still some computation efficiency like places, and also in the sensing reasoning pipeline we discussed before, there are also some intractable components unless we know some predefined domain knowledge, right? So next, briefly, I want to introduce whether we can have some intrinsic information from the data or the model itself such that can be efficiently leveraged and improve the robustness based on the principle of additional knowledge. So here is an interesting example. So as the both sensing reasoning pipeline and the game theoretical analysis are trying to solve the min-max problem. So here in this topic, I want to briefly introduce beyond the min-max problem, what's the other information we can leverage. So this is a simple example of the semantic segmentation. We show that this is a benign image, and after adding perturbation, even though to human we can see this image still look benign, but it can fool the semantic segmentation model but into segmenting this adversarial instance into arbitrary targets that we want, either it's Hello Kitty or it's a pure color or it's a street without any car. So this could be very dangerous, and if we look into details about this information, we can see that if for semantic segmentation, we know for each pixel wise, it will consider the classification result of the surrounding pixels, right? So this way, we are trying to calculate the entropy for each pixel based on the prediction of its surrounding pixels, so that we draw this heat map to see whether after adding such adversarial manipulation or noise, the spatial consistency or spatial correlation can be broken or not. And we can see for the benign image, the heat map can show very clear edges and it still show the good consistency. But with after adding noise, we can see the instance becomes very noisy, showing that the spatial consistency are broken. So based on this intuition, I want to show a very interesting example that how we can leverage the intrinsic information of spatial consistency to identify potential adversarial instances efficiently. So we can see for each image instance, we can sample two overlapped regions, and then we generate the semantic segmentation for these two regions for the overlapped part, and then we can compute the consistency for the overlapped region in terms of MLU here. And here we can see that if it's a benign instance, the consistency is very high, which is aligned with our hypothesis or observation before that the spatial consistency for benign instance is very high. But if it's an adversary instance, we can see it's clearly different with the benign one, and this separation is very clear. So leveraging such information, it is actually possible to detect such behaviors of adversarial manipulation. So we can see with this spatial consistency detection, it can achieve very high, almost 100% detection rate, even though there are adaptive attackers, showing that it is possible to identify the adversarial behaviors based on spatial consistency. And this can be further certified by looking at the consistency among the smoothed regions for each small segmentation region. So briefly, we can show this spatial consistency is a type of additional information that can be potentially leveraged to help improve the robustness of machine learning models by distinguish adversarial and benign instances. And there are other types of intrinsic information, such as temporal information or other things, can be leveraged to improve the robustness. And with this, I want to conclude my talk, which we show first that adversary behavior in real world against the machine learning model is very severe, as there are many news reporting that the stop sign example we showed before can lead to severe consequence, for example, for autonomous driving vehicles. And then we show it's possible to leveraging the domain knowledge to build up a sensing reasoning pipeline, and we can certify the end-to-end robustness for this sensing reasoning pipeline given certain oracle access for the knowledge inference. And based on more interaction between the attacker and the defenders, we can leverage game theoretical analysis to further improve the robustness of such machine learning pipeline or machine learning single models or ensemble models. And later on, we show that some intrinsic information we should pay attention to improve the robustness of machine learning model. For example, spatial consistency, temporal consistency, or other task consistency, which need additional human knowledge to try to discover or explore such potential intrinsic and extrinsic information. And thank you for listening, and please let me know if there are other questions, and I'm happy to answer them.